Hello, good morning to everyone. There is a lot of people here. Hi. We are very happy and very proud of being here with you, spending some time with this talk. As Win said, the name of the talk is Voting Between Sharks, because we are going to talk about internet voting. Yes, internet voting. And no, we are not crazy. We know what you are thinking about. We know that this room is full of security experts, and you know that any system can be considered 100% secure. And this is on the internet, so democracy is very important for being running in internet software. I mean, I know what you are thinking about, and we understand this because at the end there is a lot of ways of doing it wrong. But we are here because we want to explain you how to do it well. I mean, why we say this? Well, because we work on this, we research on this. Sandra, my colleague, is a PhD specialized on cryptographic protocol for internet voting, and I have been working for some years on security also. Actually, we work together in Cytel, which is a company researching and developing software for secure internet voting. So we have been working on this for some years, and we want to explain you a little bit about this. Well, when we talk about electronic voting, what we are talking about? There are different ways. You can use more traditional approaches, like voting machines, online voting from poll sites, where you can go to a traditional poll site using your national ID card in front of an electoral board, using a voting kiosk, maybe printing a ballot paper. But in this talk, we are going to focus on remote internet voting. The one we like the most, the one is more challenging, is the one that you can use from everywhere with your laptop and your browser, is the one that we are going to focus now. And why? Why countries are using it? Why electronic voting? We can discuss a lot of reasons. We can talk about participation, the cost. Some countries consider that it's better for one reason, or some other for other reason. At the end, it's maybe useful for people with disabilities, people in hospitals, people living abroad. I think that is for sure that it's more easy to implement online voting every 3 months, and it's better than do elections every 4 years. It depends. There are a lot of reasons. But one question, how many people in this room has ever voted through postal voting, postal mail? I did it? You did it? Okay, you know, it's crazy. It's a logistic nightmare. It's very problematic in most of countries. And what we can say about the security of postal voting is no guarantees at all. So I think that this is another reason to implement usually online voting. Sorry. And actually, there are countries which are already introducing online voting for legally binding elections, or other countries are doing pilots, are starting with proof of concepts, doing plans. So it's a trend. It's something that is coming, and we need to pay attention to that. We need to pay attention to its security. Why? Well, internet voting presents a really change of voting paradigm. Until now, you go to a traditional poll site, you can touch the ballot box. You can say hello to the electoral board. Now everything is indirect. With internet voting, you can touch only your computer, see your screen. There are a lot of intermediaries, a lot of players in the middle, hosting companies, software providers, system administrators, developers. So this kind of new indirect relationship brings new risk that we need to consider. Well, what kind of risk? What could go wrong? We can discuss about all different threats. In this talk, we are going to focus on the following ones, the ones that we consider more important or more usual concerns for people about internet voting. First of all, about privacy. I mean, privacy on the internet is very complex. We know about this. It's a real challenge in the case of internet voting. Also about trust, integrity. I mean, you are clicking with your mouse in your browser. Thanks for voting, but how can you be sure that your vote has been counted? And not only because of you trust or not trust, it's about security. What happens if you have a malware in your computer and the malware is modifying your vote? You cannot allow this in a real election, right? We need also to discuss the role of the private companies. Private companies have their own financial interests. We know it's logic, but they have a role in the election. How can we deal with that? It could be worse than companies. It could be mafias or criminal groups. And in this case, it's coercing voters, buying votes. In remote voting, it's always harder to detect when a voter is being coerced. So it's something that we need to also take a look on that. And about hacking. I mean, this is on the internet. You are going to be attacked for sure. So, and there is always someone smarter than you, a hacker better than you, that could be able to compromise your server. And then you will have someone in your server with credentials, with privilege, like a sysadmin. You have sysadmin, and you have database administrators. And these people can access to the server. But this is democracy, internet voting. You cannot accept this kind of people doing anything wrong. Oh, these are the first 7 concerns that we want to approach. They are complex. They are risky. We know that. Let's press the don't panic button, and let's go one by one and see what we can do. Please.
Thank you, Jesus. So now that Jesus has scared us a little bit with all these concerns that we may have about internet voting, we are going to go one by one and see which are the solutions that can be applied. So the first one is privacy. I think that everybody in this room is aware that privacy in the internet doesn't exist at all. Our browsers, our mobile devices are tracking our activities, and this means that not only Google, but a lot of other people know at every time where we are and what we are doing. So the question may be, how can we provide privacy to the voters in this environment? And the answer is end-to-end encryption. With this system, what we do is to encrypt the votes at the voters' computers before they are sent, using a public key, the corresponding private key of which is held by the electoral board. So the votes are sent in an encrypted form to the internet and stored in the digital ballot box. And this means that anybody that accesses the communications or has access to the ballot will not know which is the content of the votes the voters are casting. We are using end-to-end encryption in order to protect the voters' privacy in internet voting. In order to prevent the electoral board from misusing the decryption key and, for example, using it to decrypt the votes before the election ends, usually this key is split in several pieces, and each piece is provided to one of the electoral board members. After this split, the key is destroyed. And this is done before the voting phase. Then, at the end of the voting phase, when we want to obtain the results, the electoral board members will provide their pieces of the key so that we can reconstruct the decryption key and decrypt the votes. But what can happen is that one of the electoral board members forgets their piece of the key, or they just don't want to provide it in order to obtain the results of the election. This is why we use threshold secret sharing schemes. And in order to illustrate how they work, I will provide a small example. So we have a question here. How many points of a circle are needed in order to find the center? And the answer is 3. With 3 points, we can draw the circle and find the center of it. Now imagine that the center of this circle is the secret that we want to share, the private key of the election. We can take as many points of the circle as we want and provide 1 point to each of the electoral board members. And with any coalition of 3 electoral board members, we will be able to find the center of the circle again. We will be able to find the decryption key. The real system is more complex than this, and it uses polynomials in order to be able to define different thresholds. For example, that from 10 electoral board members, you need 7 in order to reconstruct the decryption key. Still, at the end of the election, the electoral board has to decrypt the votes in order to be able to produce the election results. And they will see the votes in clear, of course. And we may think, and it's correct, that our votes, even if they are sent encrypted from our computers, may contain some data that can be related to us. For example, the vote may be cast together with some authentication information, or it can be traced back to our IP, may have some timestamp information, and all this could relate an encrypted vote to the person who has cast it. Now, we want to prevent this information from being present when the electoral board decrypts the votes, because if so, they could relate clear text votes with voters and break their privacy. So now we will see several strategies that we can apply in order to prevent this. The first strategy is called the two agencies model, and in this model, there are two different services. One is the authentication service that will authenticate voters and provide them with anonymous tokens. And then there is the ballot box service, which will receive the encrypted votes from the voters, sent along with these anonymous tokens that cannot be traced back to their identities. So in this way, we are splitting the information, and we achieve the fact that we are not putting personal information with encrypted vote. The system is very easy to implement, but it has a drawback, the main drawback, that is that you need a strong assumption that these two services are independent, and they will not agree on tracing the votes with the voters who have authenticated. Then there is another strategy, which is based on using mixed nets in order to remove the information from the votes and anonymize them before we decrypt. The idea is the following. After the election, when the election ends, the electoral board takes the votes from the ballot box and removes the personal information from them. Then these votes are shuffled in order to be anonymized. And usually this is done using a mixed net, which is a network of nodes where each one applies a secret permutation and a transformation to the set of the votes in the input. Doing this sequentially, at the output, we have a set of votes that cannot be traced back to the votes, to the original votes that were stored in the ballot box. We can say that they are anonymous as far as one of the mixing nodes is honest and doesn't reveal the secret permutation it has applied. So now that the votes are anonymous, they can be decrypted by the electoral board and obtain the results without breaking the voter privacy. The main drawback of this approach is that this mixing operation can be very time-consuming. And if you want to have a lot of different mixing nodes in order to split the trust among as many entities as you want, this can take a long time. And then there is a third strategy, which is called homomorphic tally, which is based on doing the opposite that you would do in a traditional election. So in a traditional election, you will open the envelopes, and then you will count the votes in order to obtain the results. And here what we do is the opposite. We operate or count the votes while they are encrypted, and then we decrypt just the result of the election. In this way, since we are not decrypting individual votes, we are not breaking the voter privacy. In order to do that, we use homomorphic encryption systems, which allow us to operate with encrypted messages. For example, if we have a referendum where the voters could send an encrypted 0, or if they select the no option, and an encryption of 1 if they select the yes, we can operate all these encryptions and obtain the number of times the yes option has appeared. And then we could decrypt this value and obtain the result. This system is very efficient because we only have to decrypt one thing, which is the result of the election. But it poses a lot of restrictions on the structure of the vote that the voter can send. And this means that it is very suitable for referendums, for example, but in case you have complex elections like preferential elections, then it can bring a lot of complexity and it can be very, very inefficient. So as a summary, we have seen that there are a lot of ways of protecting the voter privacy in Internet voting, and the application of each of the methods in different countries, for example, may depend on the assumptions that can be done on the infrastructure, on the electoral model they have to support, or the times that you need for obtaining the results, for example. Another concern that we may have in Internet voting is about trust and integrity, because you can imagine Internet voting. OK, I click a link, I go to a website, I select my options, then I press the send button. And if I am lucky, maybe I get a message that says, thank you for sending your vote. That's it. So the thing is, how can I be sure that my vote has been counted? For example, in traditional elections, we have some kind of auditability. We can see our vote in the ballot box, and At the end of the election day, depending on the country, the voters can stay and check how the electoral board counts the votes, or in most of the cases, it will be delegated to the observers. And we can have this level of auditability also in electronic voting. For example, we can trace our votes up to the point that they are stored in the ballot box by using a public receipt. In the system, the voter casts an encrypted vote from the computer, and the server, when it receives it, it stores the vote and then provides a digitally signed receipt to the voter. The server also publishes in a public site that is usually called the bulletin board the receipts of all the votes that have been stored in the ballot box. So the voter can check that her receipt is there, and therefore she can trace the vote up to the storage in the ballot box. Of course, we will need some people to check, some auditors, to check that the server is storing the same votes corresponding to the receipts that are published. We need some kind of integrity check there. We can also trace our vote further. We can trace it up to the decryption process. In this case, we use a private receipt that is generated in the voter computer, and it is encrypted together with the vote. So both things encrypted are sent to the server, which issues a proof of validity for the receipt. This is done in order to prevent false complaints from voters that may invent a fake receipt in order to discredit the election, for example. So it's very important that we always have some proof of validity for the receipts. So the idea is that at the end of the election, when the electoral board decrypts the votes, they will recover the receipts that were encrypted there and publish them on the bulletin board. So the voters can check that the receipts are there, and therefore they can know that their votes have reached the time of the decryption. Both in the case of this private receipt or in the case of the public receipt before, these values, these receipts, are not related to the voting options the voter have selected. Mostly in the case of the private receipts, they are random values, and in the case of public receipts, they are the fingerprint or the hash of the vote, of the encrypted vote cast. This means that even if the voter has this receipt, it cannot be used to prove to a third party how she voted, for example. And then, after we have been able to trace our vote to different phases of the election, we also want to know that all these votes that have been collected in the ballot box are counted correctly, and that the electoral board or the software that they are using is not doing anything wrong. So, well, as I said before, the electoral board may do more things than in traditional elections because, for example, they may shuffle the votes for anonymizing them before decrypting, for counting them and obtaining the results. So we have all these operations, and we want to check the integrity of them. We want to check that during all these operations, no votes have disappeared or have been modified. The thing is that for privacy, we said that the shuffling, this mixing process for anonymizing the votes, has to keep the permutation in secret. And also the decryption process is using a private key. So in case you provided this secret information to the auditors in order to check the integrity of the counting process, what could happen is that these auditors could break the voters' privacy. And we don't want to trust on the auditors for privacy. We only trust the electoral board. So the question is if we can verify these processes without learning this secret information. And the answer is yes. We can do it with a very specific cryptography primitive that is called zero-knowledge proofs, which allow a prover to prove to a verifier that something is true without having to say anything else. So with this kind of proofs, we can prove that the mixing is not modifying votes while shuffling and transforming them without providing any information about the secret permutation it is applying. And the same happens with the decryption. You can prove that the decryption is done correctly and that you are not inventing decrypted votes without having to show the private key. In summary, we have seen that we have, well, a lot of verifiability in online voting because we can trace our vote up to the ballot box, we can trace our vote up to the decryption phase, and also we can check the integrity of the counting. But still, there is something missing, which is the voter computer, because the voter cannot send an encrypted vote by herself. She needs some kind of help. So the thing is that if the voter computer is in charge of generating this encrypted vote, we don't know what is there. We have to check. Because what happens if I have malware in my computer? That this computer can choose or can decide to vote for another thing. And I have to be able to detect this. For example, some of you may remember, from US elections, mainly in 2008 and in 2012, there were a lot of complaints of voters that said that the recording machines were not storing the votes that they were selecting. So they were storing other options. And this is the same that may happen in case we have malware in our computer. So the thing is that the computer is encrypting our vote. And if I want to check the content of this encrypted vote to see that it is what I selected, I have to, in some way, audit cryptographic operations. But of course, well, we as humans are limited, and cryptography is very powerful, and we need some kind of help in order to be able to audit this encryption. So I will present some methods that can be used to provide this kind of help to the voters, which will use or rely on some trusted components. And the main idea of all these methods is that as far as a small amount of the voters verify, we will be able to detect a larger scale attack. For example, the first method is called return codes, and it works like this. The voters receive before the election a voting card, usually in paper, which contains for each option in the election, the ABC, a different 4-digit code. And these codes will be different for all the voters and secret. They will only be known by them. So during the voting phase, the voter will select the voting option, the computer will prepare the encrypted vote, and then the server will compute from this encrypted vote the corresponding code and send it back to the voter. The voter can check that this code is the same as in the voting card, and because nobody else knew this code, the only way that he can receive it and matches the value he expects is because the encryption that is, the encrypted vote that is sent to the server contains what he wanted. So this can be done without breaking the voter privacy thanks to homomorphic encryption and homomorphic operations. And the idea is that when we send this encrypted voting option, we can apply homomorphic operations to compute the return codes without decrypting, just operating over the encryption. Here you can see an example of a voting card that the voters received before the election in the Norwegian elections that were held in 2011 and later on in 2013. And you can see the list of parties and the different codes that were for each party. And of course, these numbers were different for each voter. Then we have another method, which is based on auditing the vote that is generated by the encrypted vote that is generated by the computer before sending it. And in order to do it, the voter will use a special application. So the voter will select the voting option, and the computer will prepare an encrypted vote and will provide a receipt to the voter. Then the voter can decide whether he wants to audit the vote or he wants to cast it. If he wants to audit the vote, then the computer provides with some decryption information to the voter. And the voter can paste this decryption information into an audit application that will say which is the content of the vote. Otherwise, the voter can cast the vote, and then it is sent to the server, and the server will publish the receipt, as I explained before, so that the voter can check that the vote has been stored. And this is an example of the verification application. It's from the Helios voting system, a very well-known system in the academic community. And this one is specifically from the UCL student elections in 2009. And this is a sample of the kind of information the voter is presented with when he wants to audit the vote and has to paste into this application. So you can see maybe, it's a little bit difficult to understand, but there you have the randomness field, which will be used in order to decrypt the vote and and tell the content to the voter. And then we have another method, which may be the most intuitive if we think that I want to be able to check the content of the vote that I have sent. So download the vote from the server and decrypt it. And this is what this method does. So the voter selects a voting option, and then the encrypted vote prepared by the computer is sent to the server, and the voter is presented with a verification receipt. This verification receipt contains the identifier of the cast vote and also some decryption information. And then we can follow two strategies. The first strategy is to use, for example, a smartphone to read this verification receipt and ask for the encrypted vote to the server using the vote identifier. So it downloads the encrypted vote and uses the decryption information to open it and tell the content to the voter. And in case we cannot assume that the voters have smartphones, for example, we can use another approach which is based on remote decryption. So the voter can use a regular phone to enter the information in the verification receipt, and then the voting server can open the vote and tell the content to the voter. And here we can see two pictures of the two approaches. The first one is the system where you use a smartphone to read the verification information, download the vote, and decrypt it in your smartphone. And it is used in Estonian elections since 2013. And the second one is the vote receipt with which you are presented after voting with the New South Wales iVote system that was used in elections in 2015. So you could call to a special verification server that was put in place for the election, and you could tell this receipt value, you could tell the receipt value, and then the verification server opened the vote for you and told you the content. So in summary, we saw before, we can trace our vote up to the ballot box. We could trace also the vote up to the decryption process. We can check that the decryption and the counting process, everything has been done properly. And we had this missing, and we have seen that we also have a lot of mechanisms in order to be able to check that the computer is encrypting exactly what the voter has selected. We can verify all the things. So with all of this, we can say that we have end-to-end verifiability because we can verify all the steps of the process. Your turn.
Well, the next concept that we need to approach is about the role of the companies in an election. It's not only about internet voting, it's about traditional elections, postal voting, that you need to involve companies from the printing materials, the poll site, the security, the logistics, the postal voting envelopes, the software, wherever you're running. So there are companies involved, they have their own financial interests, but this is democracy. Democracy needs to be controlled by the citizens, not by the companies. We know that. How we can do this, or how we do this in traditional elections. You go to a poll site, there is a group of people, which is the electoral board. This group of people is protecting the ballot box. You cannot open the ballot box and pick up some envelopes. You cannot introduce a dozen of envelopes. No. This group of people is protecting the ballot box from anyone doing anything wrong. The similar approach we are using on online voting when we have two different votes, at least you can define more. One is the electoral board that we have been discussing during the privacy section. These people are protecting the key which is going to be used to decrypt the votes and count the votes. So they are in charge of the privacy of the election, and this is their role, privacy. The other, the administration board, they are more close to organizers of the elections. They are in charge of the integrity of the configuration, the list of voters, the list of parties, the candidates, the questions, the times and start and end of the election. Everything which is important to run the election, it needs to be digitally signed by a key which is protected by this group of people. And as Sandra explained before, we need to split the trust. We cannot provide one key to someone. No, we need to divide this key in shares using Samir secret sharing scheme. We need to store this kind of pieces in hardware tokens, which are much more stronger than files. So we can ensure that any member of these boards in their pocket can have a smart card or a crypto USB with their part of the key protected by a PIN code. Only they have 3 or 5 attempts. They select the PIN code. So the key is on their protection, is on their charge, not on the software. there is not system administrator that can access to the keys. Of course, this is cryptography. It's very powerful, but you need to provide a secure environment for all this. For instance, if you need to generate keys, it's better to do it in an isolated environment, air-gapped server, in very hardened, protected, not in the network, of course. You can do it in ceremonies with observers, auditors, local authorities, national security agencies. If you want people to protect the ceremony, you can create a good secure environment for creating this. So you ensure that only these people has access to these keys, and one single person, whoever you are in the system, an attacker, a system administrator, DBA, you cannot decrypt the votes. They are encrypted with a key. You need the share for the electoral board. And you cannot modify the electoral roll to add new voters or digitally signed results that you are inventing. No. This is a task done by the electoral and administration board. Your trust relies on these boards. They have the help of auditors and observers, but not on system, software, or administrator. No. The keys are protected by them. And what about coercion or vote buying? In remote voting, postal voting, internet voting, it's harder to detect that you are being coerced. In a poll site, you can see if someone is attacking someone for voting for them. In remote voting, is more complex to detect. And yes, in electronic voting, in internet voting, you can, for instance, record your browser session and cast a vote, prepare a video, and demonstrate to whoever that you vote for them. So you receive money or whatever. It also happens in traditional election. Now it's more easy, more cheap to buy some cameras in the watch, in the button, wherever. So you can, if you want, you can demonstrate to others about your vote. There are people that are doing selfies with their vote. So this is something that is not specific to internet voting, it's for any election. With the point that maybe in internet voting we can do more things to prevent this. What we can do for preventing in remote voting from home? Well, one approach for some countries which are more concerned to massive vote buying, to large-scale attack, is to send a one-time password to a mobile phone. So you can limit the number of 2 votes are allowed by phone. If you want to steal 1,000 of votes, you need to have 500 mobile phone or SIM cards, which is making the attack more expensive and maybe not worthy for the attacker. And maybe the better technique is implement multiple voting. If you can accept this, you can allow voters to cast in as many votes as you want. You can vote 12 times, no problem. Only the last vote will be counted. But the point is, no one is going to pay for you, to pay for your vote, if they know that 5 minutes later you can vote again. So the attacker, the coercer, can never be sure that he is really buying a good vote. Similar approach if you can use true and false credentials. Nobody is going to pay for your vote if they are not sure. If you are using a fake credential that you download from somewhere or you pick up from somewhere, it's a different kind of multiple voting approach. It's maybe more problematic from the logistic point of view, but it's also a good approach that could be implemented. And as you see, these kind of approaches are valid on internet voting, but you cannot do this on paper voting. You cannot open the envelope and no, this is my last vote. So it's a potential attack, vote buying, but there are also mechanisms to mitigate that. And then we have the Chuck Norris of the hackers. Internet voting is on the internet, so it will be attacked as any other system in the internet. And we need to accept that maybe we are good, we have good testers, we can test everything perfectly, but there is always a hacker smarter than you, someone more skilled, and you need to accept that you can be hacked. It's something that everyone in this room, as a security expert, you need to accept that your platform can be hacked, and you need to be ready for that. Of course, it doesn't mean that you do nothing. Okay, you need to accept this, but you need to work for not being hacked. You need to reduce the surface. And in the case of internet voting, we have said that the most critical activities, like the decryption, the mixing, the generation of keys, are done in isolated computers. So an external attacker cannot access to an air-gap machine with no network connection and hardened. And this is an election which is not a huge software. It is implementing maybe 3 or 4 endpoints, one for login, one for casting the vote, other for the receipt, 3 web services which are available maybe during 1 day, 2 days, 1 week for the election. If this is a specific project, you can ensure that everything is in the last version with the last patches, everything hardened. So you can do your best for reducing the surface. But anyway, we insist. We need to work with the assumption that the system could be compromised, and you can find somewhere, someday, one hacker in your platform. And then what? What happens? It's crazy. Well, it's a similar scenario when we have system administrators. We need to have system administrator. We need to have database administrator. It's mandatory, of course. But these people cannot manipulate the elections, shouldn't be able to do that. This is democracy. It's not a simple application. It's for voting. Well, we have been discussing several things. For instance, the split of responsibilities. Maybe they are administering the servers, but not the voting terminals. You can compromise a server, but not all the voting terminals or not both things. And there are isolated computers. So there are tasks in different components which ensure that the responsibility is split in different components with different environments. And additionally, we have been talking for half an hour about end-to-end encryption. So a system administrator could not decrypt a vote, because this is stored encrypted, and the key is split in pieces to the members of the electoral board. And before decryption, we are anonymizing the votes, so they cannot see anything about the voter when they are decrypted. And we are generating zero knowledge proof about the decryption, and the voters are waiting for our return code. So all these mechanisms that we have been discussing about are to protect that any internal attacker could do nothing in the platform. And remember this slide from 2 minutes ago. One single person with the secret sharing of the main keys cannot decrypt the votes. No matter that you are a system administrator, you cannot modify the electoral roll. It is digitally signed. The trust relies on the electoral administration board, not on the system administrators. So, well, if you are a malicious system administrator and you want to affect the election, what is the worst that you can do? Well, maybe the most easiest attack is to destroy everything. Delete the database, misconfigure the load balancer. Okay, you need to have backup and disaster recovery plans. It's complex, but you can do it. Maybe it's even more complex in traditional elections. If someone destroys the ballot box, in paper you cannot recover anything. But maybe the worst attack will be to replace the software. You have a very good software, so modify the behavior or replace the software. But well, we have been talking about verifiability. No matter what is doing the software, that the voter is expecting the return codes with the good option. And the decryption will generate zero knowledge proof, which are mathematical proof that everything is going well, no matter which software is running behind. So with end-to-end verifiability, we can do a software independency to verify that the election is being honest and fair. So now, as a conclusion, I'm finishing. Well, I don't want to repeat too much, but there are a lot of cryptographic mechanisms that we have been talking 14 minutes. We have compacted everything as much as we could about receipt, customers intended, isolated computers, end-to-end encryption. At the end, there are a lot of advanced security mechanisms that can be applied. Maybe it's a problem that the general public doesn't know about this, so it's complex to start the trust on internet voting. Even IT experts or security experts are not usually aware of this kind of mechanisms. But this is something that we can compare with the traditional election. It's a similar level of security. And of course, it's much, much better than postal voting. Postal voting is crazy compared to the things that you can do in internet voting. And the last sentence to close. The material is, internet voting means that it's a remote computer which is handling your vote. But doesn't mean that you need to trust on this computer. You need to verify. Verify all the things. Verifiability is the most important factor for an internet voting software. And, okay, we have played a lot of theory. We have played a lot of cryptographic operations. We have deployed a demo version of the software. In this URL, we are going to leave in the coffee room some voting cards. You have credentials. You have return code, so you can, with this URL, that is also printed here, you can experiment a regular voting session. It's a demo environment, so please be a little bit patient. The software is very simple. You need to introduce a key. You need to gather entropy first. Once you log in, you do a derivation of this key for downloading a cryptographic key pair, which is encrypted with this voting key, and then you start the login process with a challenge response protocol. I hope you can see properly. This is a traditional challenge response protocol with the server challenge, the client challenge, which is going to be digitally signed, verified in the client and in the server. So it's a traditional approach for login, using the keys that are encrypted with the star voting key. And then you can choose the best security control from this talk. This is an open list election, so imagine that they are political parties and candidates. You can select one party and candidates from different parties, open list. You can modify your vote. And at the end, once you are ready, okay, you confirm the vote. And then the vote is being sealed, is encrypted, is digitally signed. It might take some time because it's encrypting everything, it's generating the encryption of the partial return codes, which are going to be used in the server to deliver return codes while respecting the privacy. Everything is digitally signed. There are knowledge proof, not this. There's knowledge proof of the encryption. There's no proofs to demonstrate that this is properly signed. And then you will see the return codes corresponding to your vote. So if a malware modifies your vote, you will receive a different choice code. You can verify that this is what you selected, and then if you are happy, then you confirm the vote. So if the malware modified the vote, you didn't do this. But now I am happy, these are my selection, I confirm the vote, I cast the vote. This code is also derivated and is also digitally signed. So we send to the server verifies that everything is going well, that this is properly confirmed, and returns a voting receipt, which is the hash of the encrypted vote, with the signature of the voting receipt that we can use to verify, and a final code to verify that the response comes from a valid voting server. And that's all. Thanks for your time. And if you have any question. Okay. Yeah? 41 minutes.
Okay, it's a public key infrastructure, okay? But I understand how you authenticate the client, but how do you authenticate the server?
Well, there are several ways. For instance, you can run SSL, so you can, and as a user, you can ensure that the server is having the right certificate for establishing the connection. And once you cast the vote, you introduce the key, you need to receive the right return codes. So if you send this to a different malicious server, you will not receive any right return codes. So okay, you can ensure that the server is the right one. Okay? In the case of the return codes, there are
Hello, I'm Amanda Gabiam from Trusted Labs. And I guess that, okay, all the cryptographic stuff with the Shamir, secret sharing, zero knowledge, and all this stuff are strong enough. And my question is much more on Earth, because, I mean, democracy is the main concern in emerging countries that may not have all the resources to buy all the server and all the stuff around. So my question is, do you have an estimation of how much can this cost on the scale of a small country? Because, I mean, hardware and all this stuff are time-consuming, resource-consuming, and it costs a lot. Mm-hmm. So do you know a little bit how much this can cost?
Well, we work on digital security. We are not experts on the cost of this. There are some countries that has no resources, but there are organizations like the OSCE or in the Organization of American States. There are in different continents. There are countries which are helping with funds to do this kind of democracy, even more in countries where there are low level of resources, low money, so not so much money, so they don't have maybe resources enough for doing a good democracy, even on internet, on paper, because there are also problems in some countries.
Okay, so for the moment, this solution can only be deployed, I mean, in a context that, okay, all the resources that you described can be afforded. It cannot be deployed, I mean, for emerging countries.
Well, we have talked about several approaches. For example, for privacy, we had 3 different approaches, mixing, homomorphic tally, and the 2 agencies model. So, for example, the cost of implementing each one can be also one of the factors, and you can choose one that is cheaper. Maybe it takes longer, but it's something reasonable. So okay, there are different solutions for each problem, and the thing is that you can choose.
So this can be adjusted for a simple and maybe affordable for various countries.
The
The idea is.
Okay, thank
I
you.
understand this.
Thank you.
So thank you. I think time is over. Thanks for your time, and I hope you like it.
Thank you.